Hi everyone, in this video we're going to take a look at chemical activity 9. That's from Physical Chemistry, a guided inquiry, Atoms, Molecules and Spectroscopy by Moog, Spencer and Farrell. Let's take a look at the critical thinking questions. Well, when we look at the title here, it's multi-electron atoms and the subheading, why does life have to be so complicated? And the key point to this first paragraph that I want to draw your attention to is that the theoretical explanation in here of the energies and the properties of the atoms where we have more than one electron is a formidable task for scientists. In fact, it cannot be solved exactly. The Schrödinger equation for multi-electron atoms can't be solved exactly. And we're going to explore that idea with the simplest multi-electron atom that there is, and that's the helium atom. We're provided some information right up front, and we come back to seeing our friend del squared, and we see it in terms of the Cartesian coordinates in here. And then we go on to look at a description of the helium atom, and what we recognize right off the bat is that, in fact, there are three particles in here we have to think about. There's the helium nucleus. We have a +2 charge on this helium nucleus. And then there are two electrons. And these electrons are placed in the diagram some distance away from the helium nucleus. Now, the first thing we have to do for any system in order to understand the quantum mechanics of it is first to think about the classical mechanics, the classical physics for that system. And so now we have an energy, in this case it's given as U. So we're going to look at the first equation here under model 1. We remember that equation 1 is shown up here. So we're going to move towards equation 2, but we're going to start with a classical perspective. And what we recognize first of all is we've got a kinetic energy for our first electron, and we're referring to the velocity v1 in here for the first electron, and then we have a second electron and we have the velocity v2 for that second electron. So that's the kinetic energy of these two electrons, and then we have three potential energy terms in here. So R1 is the distance between the first electron and the nucleus, and then according to Coulomb's law we have the charge on that electron, and we also now have a +2 charge, +2 times the fundamental charge, which is the charge on the helium nucleus. So it therefore also makes sense to think about the second electron. So the distance that the second electron is currently away from the nucleus is R2. And in this fourth term again, we start to see the charge on the nucleus is a plus charge and the charge on the electron. So what is the final fifth term in this expression? The final fifth term, therefore, because we have two negative E charges, two negative fundamental charges, this ends up being the repulsion between those two electrons. So when we simplify further and we multiply through the terms in the brackets, we end up with this E squared term in the third term, and notice that we also have E squared terms in the fourth and fifth term here, and that's equation number 2. So we're still in the classical domain. When we next go to operators, of course, we recognize that the operator for kinetic energy that is important to us is the operator for linear momentum, or in general just momentum. And so that's written down as two del squared terms in here. So we factorized everything for the kinetic energy of these electrons into this expression. Secondly, we've now got a Z term in the effectively the third and fourth term in here. This ends up being the charge on the nucleus. It's the atomic number of the atom. So this will help us later when we do indeed need to go to atoms that have more protons in the nucleus. And then finally, we've got our repulsion, and we'll note that there's a plus charge for the repulsive energy and a negative charge for the attractive forces between the electron, each electron, and the nucleus. We've got our wave function in here, and then we have our energy, again multiplied by the wave function. It's unsolved currently, but this is our Schrödinger equation for this 2-electron species. I'm going to talk about the first few critical thinking questions while we continue to look at this model, and in fact with any POGIL exercise, those first few critical thinking questions are set up so that it pushes us to think more about the model that's put in front of us. And the first question asks us about the velocities v1 and v2, and these end up being labeled separately, and it also refers to the masses on electrons 1 and 2, and again we recognize that the masses on those 2 electrons is the same because that's a fundamental value for the electron, but of course the velocity of each of those electrons may be different. The second critical thinking question again points us towards the 2e squared term in the fourth and the third part of that equation, and this 2e squared term comes from the charge on the nucleus. It's a +2 charge, of course, multiplied by the magnitude of 1 fundamental charge for the electron. And of course we don't have the 2 over here in the fifth term because this is simply the repulsion for those 2 electrons. So Coulomb's law asks us to think about the size of the charge on each of the particles that it is describing. Critical thinking question 3 asks us to explore the negative charge or the negative value. So this is an attraction, and again this plus in here, this plus down here demonstrates that we have a repulsion between those 2 electrons. And of course I've mentioned already for critical thinking 4 that the Z actually represents the atomic number. It's the number of protons in the nucleus. If we now move down to the information on the 3rd page of the handout, what we face again is the fact that there are no wave functions that end up being eigenfunctions for the Hamiltonian operator for this Schrödinger equation for 2 electrons. And so the critical thinking question 5 asks us to think about whether this course is now over. Of course it's not. This is a crossroads, and we can now kick on and start to think about how to get around this problem. And we'll later see the importance of different approximation methods so that we can still use quantum mechanics to help us in describing what's going on in multi-electron atoms and even in polyatomic molecules. So now looking at page 80, we're reminded once again that the Schrödinger equation can't be solved, and we're introduced to this italicized point in here that there are approximate solutions which will be helpful to us nevertheless. And one particular method is known as the variational method, so we'll explore that in class. That comes up in chapter 8 of the book by Macquarie. So we now look to have a summary of that variational method. So once again, I'm going to provide you here with a process that we follow. These are the rules of the game for quantum mechanics, if you will. And so the approach is to write the Schrödinger equation as we typically do. We use the Hamiltonian that we've developed. That's really important. It is based on the classical mechanics of the system. We must start there, and then we must use the operators, the quantum mechanical operators. If that Schrödinger equation can't be solved, then we can plug in some kind of trial function, psi trial in here, and then the idea is to determine the average value for that energy. And what we will always recognize is that whatever that approximated trial solution is, we will always end up with an energy that's larger than the true energy of the system. So the trick here with the variational method is always to continue modifying the trial wave function so that we can get a lower and lower average energy, knowing that we will never get to an energy that's below the true energy of the system. And so this bullet down here basically tells us that we continue to make educated guesses. We continue to try to modify the trial wave function until we lower the energy further, and it's an iterative process. The example that's chosen in this second model in the worksheet takes us back to essentially a particle in a box or a particle in a line. And so what we can do is take ourselves back and say, well, yes, we have this particle, and this particle is p squared over 2m, and that would be how we would describe the classical kinetic energy for the system. And we also recognize that if we remember the quantum mechanical operator, that ends up being minus I h bar di by di x. And what we're doing here now is plugging this operator into the classical expression, and that allows us to come up with a Hamiltonian operator that describes this system. And again, we're recognizing that the potential energy when the particle is in the box is 0, and at the edges of the box here, the potential energy ends up being equal to infinity. So the next thing we can try is to put in a trial function. The question is, what do we do with this trial function? And the important thing is to apply this trial function to the following equation. Our volume element here, of course, would actually be dx. But what we're going to do is we're going to plug this in here. And so what we end up doing when we apply our Hamiltonian operator to the trial function, then multiply it by that same trial function and integrate over the limits of the system, a and 0, and then we divide by the square. So what we're doing in here is we're calculating the average energy. We're calculating that average energy. And what we do, and I encourage you to do this in your own time, follow that through, what you will find is that we end up with this expression here, equation 7. So let's look at the critical thinking questions. I've written the trial function already, and the first question here says, does the trial function obey the boundary condition? Well, if we plug in x equals 0, we find that indeed, because there's a factor that is x in here, we find that psi is equal to 0, and that means that indeed the probability is 0 that the particle is outside of the box at the position x equals 0. When we plug in the value x equals a, then of course this a minus a term goes to 0. So again, we find that we get a 0 value, that we find that psi is equal to 0 when x is equal to a. So yes is the answer. If we now look at question 7, so we've got the actual solution for the Schrödinger equation, and then we've got our expectation value that we had in the previous page. So of course the h squared over 8ma squared terms cancel. So we then ask ourselves, what is 10 over pi squared? And that value, actually, we put that into the calculator, ends up being 1.01. So we find that we're indeed very close. However, what we do find is that E is indeed larger. The expectation value, this average value we've just calculated with the trial functions, is larger than the energy, the actual solution of the Schrödinger equation. So the lower energy comes from the actual solution. And so this is indeed consistent with the variational principle. And we'll take a break here and move on to the next video, which will address the further critical thinking questions for this handout.